Hi everyone, my name is Dylan, and this is Team Thalia's elevator pitch for the Lifeguard bot. Let's get into it. So, our motivation behind the Lifeguard bot. According to the CDC, around 12,000 people per year drown in the US, 4,000 of that being fatal, 8,000 being non-fatal. Drowning is the second leading cause of unintentional injury or death among children 1 to 14, third for ages 1 to 44, and most drownings for younger children do occur in swimming pools. And according to the NPS, rescuing a person is risky and can lead to fatal drowning of the rescuer if not performed safely. So we determine our goal in this process is to rescue a drowning person within a reasonable amount of time, 1 minute, with as minimal physical human interaction as possible. And our target for this is going to be children ages 1 to 4 in backyard pools. So let's look at the market. There's already human lifeguards. There's the Emily rescue robot, which is remote controlled, around $10,000. There's the Coral Manta, which is a computer vision alarm system, around $2,500. And then there's a practical fence, which is $1,000 to $3,000. But all these systems are primarily, or they all require expert operators or attentive foresight. None of them are just easy to use. They all require some sort of expertise. So we want to eliminate that for the simple household. So here's an overview of our lifeguard bot. Assembled and then expanded upon. Here's a side view, seeing the look inside with the deployment system. And you can see it just how thinly our buoy is folded to be compact. There's an electronics enclosure, the wheels, rollers, etc. And then another view with the thrusters on the side, and then a closer up look at the electronics enclosure containing our batteries, our main processor being a Raspberry Pi, which we determined to be extremely reliable, voltage regulators, DC to AC inverter, MOSFET, and a charging board to recharge the batteries. So as a team, we separated our rescue into 3 simple steps: detection, transit, and deployment, all combining to be around 30 seconds for the whole process. So let's start with step 1. Robot is docked in the corner in its charging station. It receives a signal or a detection that someone is drowning. It receives that target position and then it activates. So we're going to use computer vision, a child sensing technique. There's already algorithms that have been established that detect the movement and the position of someone in the pool, determines whether they're drowning or not, and it detects the system based off that computer vision. So this will activate step 2, transit. The robot rotates, faces the target, and beam lines towards that position. And then it repeats this process using April tags to correct its position. So we're going to use April tags within the pool, 3 to 4 sets of 2 to 3 April tags. As you can see in this video, we'll have a camera mounted on the robot that will be able to detect the April tags, and as it moves, it can calculate its position relative to each April tag, which will be placed on the walls of the pool. So that'll be a localization. And then another key feature of this step is the thrusters. We need a powerful thruster that's going to get us to the position within a reasonable amount of time. So we came up with this one: 40 to 60 newtons of thrust, maximum throttle power of 645 watts. And then finally, step 3, deployment. Solenoid valve opens up, the lid pops off, and the buoy separates from the robot, inflates, and rises all within a 4-second time frame. So here's a better look at the deployment system: the solenoid valve, the CO2 canister that's going to act, or that's going to inflate the buoy, and then the batteries that power the solenoid, and then at the bottom, the inductive communicator that will receive a signal from the Raspberry Pi to activate. So, and also our production buoy we came up with this design. It's a diameter of 65 inches, so definitely large enough to hold and support a child age 1 to 5 or age 1 to 4 without the child moving off or slipping off. And then here's a relative view of how big the buoy is going to be compared to the deployment module along with the robot itself. So brass tacks, our target price, we're looking at a $2,000 price tag, which will be around a 60% markup. The price is competitive with related products in the market. In fact, it's cheaper than other products on the market and has the key features of all those products combined. So not only is it cheaper, but it does what every other product does, but in one. So that brings us to our production cost, which we estimate to be around $1,200, which we think is pretty reasonable. And our target market, of course, is homeowners with backyard pools, preferably homeowners that have children ages 1 to 4, because that would make sense, or even homeowners with pets, so in case they need rescuing. So our demographic is definitely a demographic with more disposable income, but that is still a large market. 10.4 million residential pools exist within the US, so that is still a steep market to go into. But overall, our design outcome of this project and of our robot is a 28-second rescue time, easy to manufacture, accessible, safe to use, user-friendly, materials and electronics that last years beyond a child's adolescent years, good pricing, and most importantly, it combines all the key features of products that are already within the market. So from me and everyone here at Team Thalia, I just like to say thank you for listening to this elevator pitch.